Welcome to breadboarding. In this video 16, what we're going to be doing is adding some buffer chips to the Nanocomp bus. The initial project was very simple and only had about 4 chips running off the CPU. However, it turns out that the 6809 datasheet says we can only drive up to 4 LSTTL loads. So since we're going to be adding more features such as a video card, we have a look at the diagram from the last time. This is a schematic diagram, and we can see that we've got the processor here, we've got address decoder, the ROM, the RAM, peripheral interface adapter, and the serial adapter. And what we need to do is to put the buffer chips between the address lines, the data lines, and a few of the control signals as well that we need to do. And in order to do that, what we're going to use is a couple of standard buffer chips. This is the diagram of the current system. And what we're going to be doing is now adding some buffer chips. So we're going to put a bidirectional buffer chip on the data bus. So this allows data to go both in and out. We've got the 74LS541 chips, which are easier for doing the addressed bus because all the input and output pins are all on one side or the other. This older 74LS241 chip is a little bit more awkward, but actually is more useful for the control bus because there are some signals that we need to be enabled all the time and other signals should only be enabled when the processor is using the bus. So we'll have a look at that in a minute. And for the moment, we're only going to be using the A12, A13, A14 signals, but we will add the A15 signal to the buffers because we're going to make use of the A15 signal in future videos as we change the memory map so we can use the full 64 kilobytes of RAM 6809 has. For the buffer chips we're using, the 74LS245 is an octal bus transceiver, and that basically means it can have the data going both in and out. The direction is determined by pin 1, and the read-write signal will be used from the processor to drive this. So when the processor has got read enable, it will be going, I think, from A to B, and when it's write enabled, it will go from B to A. And then the output enable will be hooked up to the bus available signal. The CPU bus available signal is 0 when the 6809 is using the bus, and so we need these chips to be enabled when this is 0, and when it goes to 1, then that means another device or another processor could potentially take over the bus, and so these chips will go into high impedance, free state high impedance. So the output enable and the 1G and these other G enable signals will be hooked up to the bus available signal from the processor. And we can see here that the 241 chip, that it's actually got the buffers are organized into 2 groups, 1 and 2. There's a separate enable signal for the group of 1 and the group of 2. The group of 1 is going to be hooked up to bus available just like everything else. So we're going to have the read write and the E clock signals hooked up there. The 2G one, we're just going to wire up to +5, so they're always enabled because there's a couple of signals. So the bus available and the bus status signals we may want to actually always have available from here. And then finally, the 74LS541, this is an octal buffer, very similar to the 241, apart from you'll notice that all the inputs are on one side and all the outputs are another. So it's much easier to wire these up onto the breadboard because everything comes in one side and goes out the other. These ones are a little bit messy, certainly for address and data bus type signals, but for the sort of control signals we're doing, then they're not too bad at all. Let's have a look at the data sheet for the 6809. So you can see here, under the address bus, it says all address bus drivers are made high impedance when the bus available is high. So that's the signal that we're using. Each pin will drive 1 full TTL load or 4 LSTTL loads. And since we're using LSTTL for everything, then that's the maximum we should really drive. And if you remember on here, we're currently driving 1, 2, 3, 4 chips. So we're okay as it stands at the moment. So if we now look at the version 3 of the Nanocomp diagram. So what I've done here is move the processor over to the right. We've now added the 74LS245. This is a bidirectional buffer. So you can see here that we've got all of the A's on this side and the B's on this side. Now the reason why we're doing it that way is because the read-write signal, when read is 1 and write is 0, and what we want is that when we're reading data, we're taking it from over here for the rest of the system and goes from A to B, and when we're writing data, we're taking it from the process over here, B to A. So in fact, the read-write signal works very well with this chip in this particular orientation. So we've got pin 1 at the top here. These other chips, so when we look at the other buffers, for these buffer chips, we need to make sure, since they're only single direction, we need to make sure that the inputs, which are the A, are on this side, and the outputs Y are on this side. And so this means that, in fact, pin 1 for these two chips would be actually at the bottom. So put a note on here, note pin 1 at the bottom for both of these buffers. So this just makes it much easier to wire up the address lines here over to this side, but it does mean that we'll be having A0 will be going to A7, and A7 will be going to A0 when we actually look at the address, the labels there, but it's much easier to do it this way than to have all the signals go around to the other side of the chip. And then the Y signals go off to the address bus and to all the other chips that we've already got enabled. And you can see here we've now wired up A15. Previously A15 was not connected. We're still not using it for anything because the address decoder doesn't take any notice of A15 at the moment, but it just means that going forward we'll be able to add A15 into the memory map at some point in time. Then finally at the top here, we've got the bus available signal coming out of the processor here. And because we've actually got a number of chips being driven by this, I've decided to put the bus available signal through the other buffer. So buffer 2 here, and you can see we're actually feeding this into the buffer 2 A4 value, and we're then actually taking the output for 4 from here, and we're feeding that onto and this bus available signal then also goes to all the other buffer chip enables, so that we can keep on adding more buffer chips if we need to going forwards, and we don't have to worry about overloading the processor here. The bus status signal is not directly used, but we will use it sometimes when using the logic analyzer, and I tend to trigger the logic analyzer on the bus status signal. We might consider putting this out through the second block of buffer here, but for the moment I don't think we need to worry about it. So that's what we're going to be doing. What I'll do is to speed all this up. There were a few in the first run that I did of this. I did make a few little mistakes, and I did put some of the chips in the wrong way around. So I've actually corrected that in the final bit, but you may see where we're putting some of the wires in may not make quite sense if you altered it and looked at it. But I think the final result will all be working and matches this version of the schematic. And what we're going to be doing here is removing some of these jumper cables that we did in the early stages. And the reason why we did these jumper cables is because we're going to be putting another board in here, and this is where the buffer chips are going to go. Once we've got the buffer chips in there, we might still use some of these cables for doing some of the things, but we're going to have the buffer chips in the middle there. Okay, so we've got our board here. What we're going to have to do first of all is just to unplug some of these. So I think I'm going to unplug it from the bus side over here. So just going to unplug those cables. We're going to unplug the data lines as well. Okay, so we've got those. There's a few of the control signals. So these are the interrupt lines and the reset E pins. We have some power as well. So again, for the moment, we'll just unplug the power there. And then we just got a few of the power connections here. So let's just unplug those for the moment. Those were really being used to also hold the board together. Then finally, we've got these address lines. So this is the A14, A13 and A12 address lines. Now these are obviously going to be replaced with new outputs from the buffers. And what we're also going to do is we're going to need to add an extra rail or two down the bottom here for the address line. So at the moment we go from A0 up to A11. We're going to need to add A12, 13, 14 and 15 going. So we're going to need to have another 2 power rails here to add those extra address lines. Okay, so that's the board there. We can actually move the rest of these out of the way whilst we're working on this. And what we've got here is another brand new breadboard, and what I have done is, because I don't want to have 2 lots of power rails next to each other, you can go through, for these breadboards, do actually have the power rails joined on the plastic at the bottom here, or the sticky stuff. But if you run a knife down the gap in the middle here, apart from obviously where the tabs are, you can actually run a knife through there and then run a knife along the back, and then it will come apart fairly easily. So this means we've got this comes apart. We can use this for one of our power rails down the bottom here, and we can now also match this. So we've got 60, 60, 1, 1. So we've got them the right way around. And the only issue with the soft sort of sticky rubber foamy stuff is that sometimes it makes it stick together. But anyway, so we've been able to hook those together. And what we're going to want to do now is to work out what layout we need to ensure that we simplify our layout as much as possible. So we've got our chips here. So the 745 is for the data. So we probably want to make sure that our data outputs, which are going to be, I think the A is going to be. So let's just see where we are. So we've got D7 is there. So really you want A8, D7, A1, D1. So that's going to be fairly close. The only issue we've got here, we also need to fit in our chip for our other control signals. I'm not sure if we've quite got enough space there. So we don't appear to have quite enough space there. So I think what we're going to have to do is to move this down a little bit, and we're going to end up with some of the signals going up here. But the nature of these power strips is that they're a bit spread out anyway, so we're never going to get all the control signals completely in line. So let's just move this down a couple so that we allow the power to go direct to the side there. So if we allow for that, we've got power going to there. We'll leave a gap between there. That should be fine. So you can see here that our A8 here is going to go to there, and our A1 here is going to be going up there, but that's not going to be too bad. And then we're going to have 2 signals here going up to the E and the read write. That's not too bad. And then down here we're going to perhaps be able to do the address signals a little more easily. So we've got A0 there, and A0 is going to be coming here. So we can perhaps make this one a little closer. Yeah, and then the other address signals, we can put that there, and just make sure that our power lines are lining up. VCC there, ground there, VCC there, ground there. So yeah, that will line up. And we're going to require to have our address lines coming round here down to here. All these address lines here are going to go to there, and then we're just going to need to bridge these across here. And rather than using these jumper cables, certainly for the address lines, we're just going to use hardwired green wires for the address lines. Whether or not we continue to use the ribbon cable for the data, it might be easier than trying to get 8 data lines going around here. So I think we might still use this one. So what I'm going to do now is just to run through the speeded up, wiring this up, and then we'll come back and actually just have a quick look at the board and explain what we've done. Okay, so what you can see here, we've got our 2 address buffers down the bottom here. These are being driven by the output of the bus available signal, which is going up into this permanently on buffer here. So that signal is coming out of there and then is then driving the first buffer on this particular chip. It's also then connected to the bidirectional data buffer and then back down to here. We can see we've got A0 through to A15 all hooked up to here. We've got the address lines all hooked up onto the bus here. And then we've also got the data lines all the way going up to the data lines on the bus here. I've continued to use this jumper cable to connect the D0 to D7 lines over to here. I might change it because these cables do occasionally become loose, and if the data bus becomes loose, then that is going to cause problems. So I might look at rewiring this at some point in time and put a block of permanent wires, but it means moving the clock circuit around and doing a bit of messing around. We've also got the read write and the E clock signals coming out to this control buffer here. So these signals are then going off up to the rest of the circuit because they're being used by all these other chips. So this is the buffer circuit. We're also wiring all the unused buffers. We're wiring up to +5 volts. The inputs for those are wired up to +5 volts. If we needed to, we have a number of buffers still available. These ones are permanently enabled. These ones are only enabled when the processor is using the bus. So what this means is that as we want to add our video card and other features to the Nano Comp, it means we continue to do so and we don't have to worry about overloading the chip or damaging the chip. So that's a fairly quick video. I will be following this up with another video fairly shortly. So we'll be looking at improving the power distribution on the board, because as we start to add more breadboards like we've just done, the power connections and power distribution becomes much more of an important issue. And in fact, when I was building the buffer boards, I had two jumper cables that I was using for the power, and I found out that these were actually faulty and were causing some problems with the power. So it just goes to show that you should always check your power distribution out whenever you're doing these sorts of breadboard projects. So in the next video, what we'll be doing is looking at the power, and also we'll be looking at changing the memory map so that we can make full use of the 64K available. In order to do that, we'll be using a programmable logic device. So the PLA, or a GAL as it's sometimes also known, is a programmable chip which allows us to do configurable address decoding and is a lot more flexible than using hardwired logic. So we'll be going on to that in the next video. So I hope this short video is of interest. If you want to not miss out on any other videos, please hit subscribe. And if you found it useful, please hit like. Thanks very much. Thank you for watching.